Okay, so suppose that y equals f of x has a stationary point at x equals a. Both f of a and f double prime of a don't equal 0. Let g of x equal 1 over f of x. So we want to prove that the graph of y equals g of x also has a stationary point at x equals a. So we know that f of a does not equal 0. We know that f double prime of a does not equal 0. We also know that we have a stationary point at x equals a. So that tells us that f prime of a does equal 0. We're trying to prove that we also have a stationary point on g of x at x equals a. So we're wanting to try and prove that g prime of a equals 0. So let's take our function, g of x equals 1 over f of x. And let's put it in a form where we can use the chain rule, make it a little bit easier. G of x equals f of x all to the power of minus 1. So then we can go g prime of x equals minus f of x to the power of minus 2 times f prime of x. So we've got it in this form. Let's put it back into something a little more manageable, which is minus f prime of x all over f of x squared, which looks a little bit like our proof of the quotient rule. So let's sub in our a's to see what's happening to our derivative at a. So g prime of a equals minus f prime of a all over f of a squared. So what do we know? We know that f prime of a must equal 0. So that's going to be 0. And we don't know what f of a is, but we know if it's squared, it's just going to be, we can just say it's going to be some positive number. So I'm just going to say some positive number, which essentially means 0. So g prime of a equals 0, which is what we were trying to prove. G prime of a equals 0, thus g of x has a stationary point at x equals a. Let's do a little square. All right. Second part of the question was show that the stationary point. At the stationary point, the sign of g double prime of a, the second derivative, is the opposite to f double prime of a. So we're going to use the quotient rule this time. So let's take our first derivative, which we discovered was minus f prime of x over f of x squared. And let's take the second derivative. So we're going to use the quotient rule, which I have my little note up here for. And I've done this earlier, so I don't have to. What we're going to get is minus f of x squared, f double prime of x, minus 2 f of x, 2 f prime of x, and we have another negative in there, so that's going to be positive. It's going to be all over f of x to the power of 4. And we can simplify this again by factoring out the f of x. So take the f of x out. and we're going to switch these over. So we have 4 f prime of x minus f of x f double prime of x. It's all over f of x all to the power of 4. That's going to cancel, so we can say 3. Now let's sub in our a. So we know that, well, this is going to become 0 because we know that f prime of a is 0. So we're just going to write 0 here. And then this is going to cancel as well. Because this is gone, so it's going to cancel. So we're going to get is f double prime of a, oh, that's a negative, all over f of a squared. Again, this f of a squared we know is just going to be some positive number. So whatever g double prime of a is, it will give us a negative of the f double prime of a. So this is some positive number. So g double prime of a equals some negative f double prime of a over something. So what that tells us is that that whenever the concavity of g is positive, the concavity of f will be negative, and vice versa. So the last part of the question, we're just going to take that y equals f of x looks like this dark one here, and I've already sketched out y equals g of x, which is 1 over f of x, and we found that the stationary points for f of x will be the same as g of x. So we've got a stationary point here at 2 where f of x is 0. F of x is also 0 here, so g of x will also be 0, and we'll have a local maximum at 3, 1 for g of x, because 1 over 1 is 1. And we're going to have a local minimum at 1, and 1 over 2. So this local minimum for g of x is going to be at the point 1 half. And then we have another point here where f of x crosses the x-axis. And this is going to lead into the second part of the question, the follow-up question, which is, can g have any other critical points justify your answer? Well, critical points happen where you've got the first derivative equal to 0 or undefined. So at these stationary points, g prime of x is equal to 0, as we have a maximum and a minimum. The other way you can have a critical point is if the derivative at the point is undefined. So we're going to have a situation where f of x must be equal to 0 for it to be undefined. So f of x crosses the x-axis here is equal to 0. So you get a situation where the derivative is also where the derivative of g is undefined, because we're going to have a 0 here. G prime of x equals 0 squared over something undefined. And what happens at this point is the graph of g of x will shoot up, and then we'll shoot back from negative infinity after minus 1 over 3. So that's your third critical point there. I think that's it. Thank you.